Laser.
There's one on the table.
On the table here. Okay. This looked like a aircraft flare or something. Okay, good afternoon. I'm going to start the presentation and all my group members will join. Our self-affinity group is called MuST-ACT, standing for Multisensory Tools for Active and Creative Thinking. And we have teams across many engineering disciplines and from multiple universities. And our mentor is Darryl Pines. So what we've all realized, and I'm preaching to the choir, is the challenge is most of the engineering analysis, design system integration are often confined, limited to theoretical tools. And many of them are two-dimensional. And so what we are proposing to do is, our MuST-ACT affinity group, we would like to take concepts and make them physically real using multisensory tools. Because different people learn the subject areas are based on different sensory organs and different fractions of that. And what if we can have tools that integrates a number of these sensory organs so it helps the students learn because they can use the tool that is more appropriate to their style of learning. And when you take the human ways of learning, we use sensory organs for sensing and for watching and thinking and actually doing. And we have the left part, which is more analytical, and the right part that is more artistic. And it'll be great if we can have different engineering tools that can be integrated, and we can foster multidimensional thinking, modeling, and also include hands-on creation. So what brought us together was each of us were interested in design or helping teach students spatial three-dimensional visualization. For example, we have Lily in our group who was interested in designing this object, and Aaron was interested in understanding how you can minimize the number of iterations you can go through. In the ideal world, once you come up with the design criterion, and sure enough, you can freeze the design criterion and it works perfectly, but that is not what happens in real life. And as you freeze the design and you start doing the modeling and start using it, you find that there are problems that we had not anticipated. So we have to go back to the drawing board and fix those problems and then keep on doing this in an iterative manner. And this is a solar cell based lamp that Ismail's group had printed using 3D printing. So using these kind of additive manufacturing tools can really help students have hands-on learning and also speed up the iterative process. So some of us are interested in this creative iterative design. And then we have Robert interested in low-cost experiment. Here's the Venturi apparatus that he fabricated using 3D printing. This is not the picture, but he has some fabricated using 3D printing. And basically, the fluid flows through that, and at different points, he had put pressure gauges. And he can measure the velocity, and he can measure the pressure. And the students can learn the Bernoulli principle by using this apparatus. And so we have an ability to use this additive manufacturing to build low-cost experiments that the students can really do hands-on in the laboratory. And then personally, a couple of us, we are interested in haptic experience. Jenna was interested in this haptic paddle that is used to teach systems engineering. For example, if you have a wheel with brakes in it, so how do you model that system as a stable system versus unstable system? Or a big building, when you have an earthquake hit the building. So how can you model it so that the building is stable? So what are the stability criterion? So using the haptic experience, one could do that, and Jenna had designed this little apparatus where students can actually feel the touch and push of that. And such an instrument can also help, for example, visually impaired students learn by feeling and touching what's going on. And my own interest comes from material science, crystallography. A lot of students have difficulty understanding and relating to three-dimensional structures and objects, especially crystal structures. And for example, if we can have digital models that could be printed in a 3D printer, regular students can actually feel them and understand what the crystal structures are. And crystal structure is the easy part of it. When you have materials, you have a lot of defects in materials, and you have very, very complicated structures for them. So how do you use 3D printers to teach those fundamental concepts and fundamental processes? And you also have LE interested in teaching spatial, 3D spatial visualization using iPad tablets. So all this we grouped under haptic experience. And so this was a natural group, and it addresses a problem that most students start off saying that, well, I'm creative. Then after trying out a bit, they say, well, I'm not creative, because they have difficulties because the learning styles did not suit them. So our interest in multisensory tools can help foster active and creative thinking and learning among a very diverse class of students, and also bring in differently abled students into science and engineering disciplines.
So, okay, so take a few minutes now and visualize the tetrahedron. Actually, take a few seconds and visualize the tetrahedron. Everybody got it? Who doesn't know what a tetrahedron is? Okay, good, excellent. Okay, all right. You have 4 paper clips and 3 straws. Pair up with somebody near you, or you should have 4 paper clips and 3 straws. Pair up with somebody near you and build a tetrahedron.
Took a long time? Oh, sorry. Yeah. Somebody should have passed me. Try to discard it. Sure.
Challenges and the like, and then. Wow.
I know.
All right, 10 seconds.
9, 8, 7, 6, 5, 4, 3, 2, 1. Time's up.
You can keep building, though. We're going to move on. All right, so we wanted to talk about kind of the implementation challenges that are involved with making actual things in the classroom, right? And so the first thing is that we have to balance expense and robustness. Obviously, we had to sort of scavenge things that were very inexpensive. Your tetrahedron's probably not particularly robust, right? Students get frustrated if the methods that they use to build stuff lead to things that break easily, right? But we can't be spending infinite dollars on these kinds of initiatives, right? So also, how do we bring the appropriate tools into the classroom that enable us to make things effectively? Because ideally, we want to get away from this job shop mentality that says that engineers just design things and then they hand them off to someone else to make them, because there's an interplay between the methods you choose to make things, the materials that you choose, and when you break that feedback cycle of prototyping something in different types of materials, right, you lose the understanding of that interplay. Of course, resources are very, very tough, right? What tooling can we make available? How do we use spaces effectively? You probably don't have ownership of your classes to just leave stuff in there, right, when you're not teaching in there. And of course, consumables are always an issue, which leads to this issue of sustainability, right? If we want classes where students are making things, prototyping, learning iteratively, how do we sustain that effort? Because those are expensive in terms of our time and in terms of the physical resources that are required.
And then just briefly, we talked some about what worked well for us. And I'd like to start with the goals. So some of the things that we want the students to take away from doing things like what you just did with the tetrahedron is to engage sort of creatively with materials and with creative thinking tools that are often based on modeling and playing and that sort of thing. To really engage the students with multiple senses, work on the concept of embodied cognition, and sort of identify develop their identity as sort of creative individuals. So give them creative confidence that I'm an engineer and I'm creative. Some of the different strategies that we talked about were using open-ended problems, encouraging mistakes. The classroom is a really great place to make mistakes. You can learn from those. And things like critical and creative thinking. And some of the things that Srini already talked some about, some of the ideas that we had, portfolios, posting their projects on LinkedIn, remote labs, and these are some things that we're actually doing now, hybrid delivery, the haptic paddle, and a 3D spatial visualization app as ideas of things that we're doing now to do that. We're trying to move forward also and see what else we can do.
And then the next challenge we discussed was sort of how to document impacts, right? And we sort of divided this up into two realms of impacts within the classroom and then impacts beyond the classroom. And there's been a lot of us who have done sort of different types of assessments, whether they're quantitative, anecdotal, qualitative in the form of focus groups. And then outside the classroom, there's been a lot of work in sort of leveraging open source and online resources, such as app markets, our websites, putting together online video tutorials. Of course, the traditional dissemination through conferences and journals, and then symposiums like here. And then the last thing we discussed was scalability. And so the goal really is to take our technologies, our tools, leverage what already exists, and then send it off, right, beyond just our classroom to broaden the impact and the sustainability. And most of us determine that we're sort of at our course or our multiple course level. And really where we want to go is much beyond that, into multiple domains, multiple institutions, right? Or into more informal settings where homeschooling may occur, or working with hobbyists or individuals. I mean, we talked about several methods, primarily establishing these interdisciplinary collaborations to do this.
So what I wanted to talk briefly about, to sort of summarize what we've done, it took us a while to find our affinity group, and I think over the course of the discussion we found there was some natural cross-disciplinary curriculum development. So some of us were developing tools and resources that could teach topics that we could relate to, such as using the haptic paddle, or I do some shake table, developing models using tabletop shake tables to understand dynamic principles, or using the haptic paddle as a case study to teach mechatronics. So that was a natural fit. But I think all of us fit under this umbrella of 3D modeling, visualization, and rapid prototyping as learning tools to enhance education. So how do we bring creativity into the classroom? How do we use sensory, tactile, tangible, hands-on things to teach 3D visualization? So, a lot of us are looking at 3D printing or the iPad app to teach 3D visualization skills, to develop tools to help visually impaired students. And how do we use these tools for rapid prototyping and in order to enhance the iterative design approach? So gain feedback and iterate. And And so one of the last things that we wanted to do was develop a workshop to explore these issues across disciplines, because we come from multiple disciplines, and an area where we could see, are there tools already out there that we could all leverage and work together in order to do this?
Thank you.
Feisty turtles. That was really great, and I like the idea of iteration and design. So how would you go about assessing whether or not students understand the concept and are able to apply the concept of iteration and design?
One thing I like to use is reflections and having students, putting students together in a smaller class, but in a smaller focus group, to have them reflect on what were the critical sort of learning incidents that you experienced during the class. And a lot of times when you do that, you come up with, I was really frustrated whenever we were trying to work on, build that tetrahedron and couldn't get the materials to work and that sort of thing. And so then you can use that as sort of a learning opportunity for them to figure out what they actually learned from experience in that maybe frustrating moment. Something I did.
I think one of the things that we're also interested in is this idea of an engineering portfolio. And so as students iterate, they're building up this engineering portfolio, and presumably you can use that sort of at the end for summative assessment of their progress, where you should be able to see improvement in their design process and the outcomes through their engineering portfolio, kind of tracking their development.
And many of these designs also have quantitative parameters.